Hello and welcome to the third Orcad tutorial on how to implement a silicon carbide base buck converter with the parameter of 500 volt input and a output voltage of 200 with a current output of 10 amps at 500 kHz. In this video, I will be implementing the dual power supply topology. Please watch part 1 of this series to make sure you have properly imported the components we will be using in this video, as well as watch part 2 to see a more detailed tutorial on making one of these silicon carbide based buck converters. So let's get started. Open up Orcad and create a new project. We will call this dual power supply. Make sure the first selection is clicked and pick a location. Let's just save this in documents. Hit OK. Create a blank project and it will create a clean schematic page here for you. Click place, part. As I've mentioned in my past videos, quick way to find any component that you've already imported into your library is click on Library, Control A to select all, and we will find our gate driver, UCC 21520DW. Make sure you don't use the design cache version of it. Next, we will get our silicon carbide MOSFETs, SCT316KL. If you do not have any of the components here, please watch the previous videos as I show you how to properly import them. Just double click and we will place 2 here. I am going to populate this schematic, so I will be back. And I've populated the schematic here. I'm going to show you how to find all these components inside the libraries you already imported. So first off, let's find the inductor. Make sure all your libraries are selected here. Go ahead and just press L, get the analog of it, and there's one of your inductor currents. For your capacitor, just use the analog, press C. Next, a resistor value, just input R. We also need a diode, 1N1183. We need a voltage DC source, VDC. And we need 2 types of ground. We need the ground on the digital side and we need the ground on our actual circuit. So an easy way to get to this is go ahead and just click this ground symbol here. And we need 2 types. We can just select this one. And let's get our second type now. Oh, that was the same one. Let's get the ground signal. So grounds can be kind of tricky, but you need to remember that you just double click on it and it'll open up a property editor. You want to change the name to 0. You're going to get an error about your ground if you do not set this as 0. So you want to save and just close. It's just asking you, are you sure? Just keep clicking yes. Just close this tab here. Same concept goes for this ground. You want to change the name to 0. If you just click close, it'll ask if you want to save it. And it did save it. Yep. Those are the two grounds we will be using. And lastly, let's get our digital signal. So for the digital signal, just type in DIGSTIM1. This represents the digital signal for 1 bit. So it's either 0 or 1. Just double click, and we'll need 2 of them. One for the high drive PWM input and the low drive PWM. I'm sorry, the low side PWM digital signal. And those are all the components that you will need to create the dual power supply topology. In discussing the silicon carbide MOSFET, notice that this configuration does not match this configuration. I've previously discussed how there is coding embedded in these components, and the computer will know which one is the gate and which one is the drain and which one's the source. It's actually in alphabetical order. So we have the drain, the gate, the source. And no matter how this is configured, the software will know which is which. But if you want to keep in this configuration to make it more neat, you can right click on the component, edit part. It'll take you to a part editor. You want to just click on the line here. Let's just call it some arbitrary value, 22. The pins don't like to be the same values at the same time, so we can't switch them. So we set 1, 2, 3. Let's make this 2. One. 3. And just close it, and it'll ask you to update it. Hit update, click yes, and it's updated. And let's just use this one instead to prove that it's not embedded in the component itself, but you can just easily change it yourself. Let's see, next is wiring. So let me walk through that with you. Similar to our previous topology, we're going to hit W, connect the VCC eyes together to the 15-volt input. Go ahead and connect the digital PWM's signal. These two will be connected to ground. Make sure they don't connect. You can actually overlap, but if it stays red when you leave it, you know it connected. But if I just hover over it like this, it did not connect to that wire. Just connect to that node and just connect it. Next, we'll connect this to the dead time. Oh, this wire is actually not supposed to be there. Also connect to disable wire connected to ground. So make sure you just name these as INA and INB. We will use this as references later when we set up the digital signal. Go ahead and connect that to ground. So the left hand side, the digital side, is set up here. Next, I will show you how to do the wiring on the right side. So here are our dual power supply, providing positive and negative voltage supply. I'll just connect these guys like this. Put them in series. Same goes for the load drive side. Connect these nodes together. We want to connect VDDA to this node on top. Same for VDDB. The no connects NC, just connect them together. Next, similar to our previous topology, just put these guys in parallel with each other. Connect out A. Connect the source to ground. let's not forget this node here, VSSA. And that is our completed topology of the dual power supply. Let's make sure all the connections are correct. Everything seems to check out. Now we are going to create a new simulation here. Simulation 1, create. For this one, we don't have to click the skip initial transient bias point calculation. Let's just do 100 microseconds. But we do need to make sure that we go into options and make sure to click on auto converge. It will create an error if you do not put these settings on. And going back, before we start our simulation, there are 3 files that we have to add on. First is the library file. We can browse for our 2 real components that we used. It's very important that you know where you save them because you'll always have to refer back to them. For this one, this was saved in downloads. It's a .lib file. This is the MOSFET. Go ahead and add to design. Next. And go back. For the gate driver, add to design. Next, we need the stimulus file. The stimulus file provides a digital signal, a PWM digital signal to our gate driver. It controls when the MOSFETs turn on and off, essentially. So actually, we just need to hit edit. It'll prompt an editor. Do file new. New stimulus. Remember the reference names that we set them in A, clock. Make sure it's frequency and duty cycle, 500K. We set at 0.4 duty cycle. And next for second digital signal here in B. Same thing. For this one, same frequency. The duty cycle will be 0.6 instead, and the initial value will be 1 instead of 0. Notice there's always at least one MOSFET on at any given time. It's exactly what we're looking for. Go ahead and just save this in a location. Hit save. Let's browse for it. This PC. Add to design. Hit OK. Next, we will just put probes on our schematic. We want to know the voltage output. Let's also take a look at the PWM signal. And let's also look at the current output. And go ahead and press Run Spice. Hopefully no errors. I'll be back with the results. This is the result you should get. although there is something wrong with the waveform. Notice our voltage here. It says L1 because it's getting the voltage at the inductor, which is also our voltage output, and it's showing that it's 185, so it's not quite at 200. Looking back at the schematic, I noticed I made an error. These two nodes should not be connected. I'll go ahead and run the simulation again, and I'll be back with the results. Here is the second attempt, and we are almost at 200 volts as desired, and we are at 9.98 amps. And notice if we zoom in here, exit the cursor, right click, zoom area, this is the PWM signal, and it shows us the voltages of when it turns on and off. And that's it for this video. Thank you for watching.